Hello, and thank you for joining me again for another tutorial on deflection using the double integration method. In this tutorial, we'll look at a simply supported beam with a concentrated moment and see how that differs, if it does at all, from the other beams that we've solved. For this example, let's consider a simply supported beam AB with a uniform cross-section and a span length of L. The beam is supported by a pin at A and a roller at B, and it carries a concentrated applied moment, ME, at the right-hand end, as shown. Our task is to determine two things: the equation of the slope along the beam and the equation of the elastic curve. This example is short, but it's a really useful one for exams because the loading is not a force, it's a pure moment, which means the bending moment diagram has a different character to the cases with point loads or distributed loads. We will follow the same double integration framework as before. Let's remind ourselves of the framework. We assume that EI is constant along the beam, and we start by sketching the expected elastic curve, using the boundary conditions to guide the shape. We then use the method of sections to write the bending moment expression mx as a function of position x. In this example, the loading is a pure end moment, so the moment expression will be particularly simple once the reactions are found. We integrate the moment once to obtain the slope, and then a second time to obtain the deflection equation, including the constants of integration. Finally, we evaluate those constants using the boundary conditions at the supports, and then we can compute slope and deflection at any point along the span. So let's start off by sketching the elastic curve. The beam is simply supported, so the vertical deflection is 0 at both supports A and B. The applied moment at B causes the beam to rotate at that end, producing curvature across the span. The sketch reflects this behaviour with no displacement at the supports, but a clear change in curvature driven by the end moment. Let's move on to the bending moment behaviour. Because the beam carries a concentrated moment at B and no distributed loads, the bending moment varies linearly along the span. Before we begin, we need to determine the support reactions using equilibrium. Starting off with horizontal equilibrium, there are no horizontal forces acting on the beam, so AX equals 0. Next, we take moments around point A. So first we have the reaction force By times the lever arm L, producing a positive moment in our sign convention, and then minus ME, which is a pure moment, so doesn't need to be multiplied by any distances, and all of that needs to equal 0. Isolating By gives us that the reaction is ME over L. Finally, we apply vertical equilibrium. Since there are no vertical forces acting on the beam, the vertical reactions must balance each other out. So AY must equal minus BY, and since we know BY, we know that AY equals minus ME over L. With the reactions now known, we can move on to writing the bending moment expression as a function of position along the beam. We set up the free body diagram and identify the bending moment behaviour. From the previous slide, we know that the applied end moment, ME, generates equal and opposite vertical reactions at the supports, and we can draw them into the free body diagram. With this in mind, we introduce a coordinate x, which we measure from the left-hand side at support A, and we can see the resulting bending moment diagram on the lower sketch. Because there are no distributed loads, the bending moment varies linearly along the span. It starts from 0 at A and increases steadily to the value of ME at B. This linear variation confirms that the bending moment at any point along the beam can be written as a simple function of position, and in the next step, we will use this expression directly. So to derive the bending moment expression, we use a section cut. As we mentioned before, x is measured from the left-hand support A towards B, and we'll consider a general section between A and B while we know that x is between 0 and L. Cutting the beam at a distance x, drawing the free body diagram of this section, and then we will do the moments around the cut. So you can see here, when we draw the free body diagram, all we have is the reaction force at A, ME over L going downwards, and we have then in purple the internal forces that we've just exposed. So doing the moment around the cut, we get the moment that we just exposed, plus, because in our sign convention, that downwards reaction gives us a positive moment, ME over L, which is the reaction force, times x, which is the lever arm, and that needs to equal 0. Rearranging this, we obtain the bending moment expression, which is minus ME over L times x. Next, we apply the double integration method to obtain the slope and the deflection equations. We start by integrating the bending moment expression that we just found once to find the slope. Substituting minus me over L times x and integrating gives us minus me over L times x squared over 2 plus the constant of integration c1. This is the general expression for the slope, including the first constant of integration. And we can take that expression and integrate it to receive an expression for deflection. So integrating that expression again gives us minus me over 2L times x cubed over 3 plus c1 times x plus c2. And if we multiply the 2 and the 3 of the first term, we get minus me times x cubed over 6L plus c1 times x plus c2. At this stage, we have the general expressions for both slope and deflection, each containing unknown constants. We'll determine those constants next using the boundary conditions at the supports. Because the beam is simply supported, the vertical deflection at both pin supports must be 0, and that gives us two boundary conditions. So the deflection y, when x equals 0, so we're at support A, has to equal 0, and when x equals L, so we're at support B, the deflection y needs to be 0. In this example, there is only one region, so we don't need any continuity conditions between segments. These two boundary conditions are sufficient to determine two unknown constants, c1 and c2. So we always need the number of equations to match the number of unknowns. Let's start by applying the first boundary condition to determine the constants of integration. As we said, at the left support A, x equals 0 and the deflection must also be 0. So taking first our original expression for EIY, we then substitute x equals 0. All terms involving x vanish, leaving only the constant term, and from this we can immediately obtain that c2 equals 0. With c2 determined, the deflection expression simplifies to minus me times x cubed over 6L plus c1 times x. We now apply the second boundary condition at the right-hand support B. Because the beam is simply supported, we know that the vertical deflection when x equals L, so when we're at point B, has to be 0. So once again, we start with that reduced equation for EIY, and then we substitute x equals L. You can see here that this replaces x cubed with L and x with L. We can divide both sides by L and then isolate C1. And as you can see on the slide, we remain with C1 equaling me times L over 6. At this point, all the constants of integration have been determined. The slope and deflection expressions can now be fully defined. And here are the final results for this example. The expression at the top gives the final slope equation. Dividing through by EI would give us the physical slope theta. At this stage, it's good practice to pause and check units. The slope must be dimensionless, which confirms that the form of the equation is consistent. The boxed expression at the bottom gives the final deflection equation. This is the complete expression for EIY, incorporating both boundary conditions. Again, dividing by EI would give us the deflection y at any point along the beam. Because these results are written in parametric form, they are very powerful. Once the applied moment ME, the span L, and the flexural rigidity EI are known, the slope and deflection can be evaluated at any position x along the beam. This example is also a good reminder that even for relatively simple loading cases, keeping your algebra organized and checking units at each stage is essential for avoiding mistakes and building confidence in the final result. Let's see how we can use the expressions. So let's evaluate the slope at the left support A. We'll start off with the slope equation that we found already, and then we can substitute x equals 0 into the equation. Any terms involving x vanish, leaving us only with a constant term. This gives us the value of EI theta A, and if we divide by EI, we then get the physical slope at A. The final result shows that the slope at the left support, theta A, equals me times L over 6EI. And this confirms that even though the deflection at pin support is 0, the slope is generally non-zero. We can also evaluate the deflection at midspan or indeed any point along the beam. But looking at midspan, we can substitute x equals L over 2, and that corresponds obviously to the midspan of the beam. If we substitute it into the first general equation that is presented at the top of the slide, we can find that the deflection at midspan is me times L squared over 16EI. Let's just note the sign in this result. In this case, the deflection is positive, This indicates an upward deflection, and that is consistent with the curvature produced by the applied end moment and the sign convention we adopted earlier. As before, this result is given in parametric form, meaning that once the material properties E, the second moment of area I, the span L, and the applied moment ME are known, the deflection can be evaluated directly for any simply supported beam with a concentrated moment at the end. I hope you found that helpful. If you have any questions, please leave them in the comments. And I hope you join me again for some more structural engineering.